So now we want to start kind of connecting these power series to actual functions. So I said at the beginning of the last video that we're kind of building up towards being able to represent most functions as a infinite series of polynomials. And if you notice, the definition of the power series is just a series of polynomials, right? Because you just have these powers of x, right? So these are the polynomials that we're kind of working up towards. So I just want to look at a one that we can kind of get with the stuff we already did first, and then we'll do more of these after we start talking about Taylor series. But there's one that we can get right away. So let's consider the geometric series. Okay, in terms of this x, let's look at this one. 1 plus x squared plus x cubed, okay, which is going to be equal to just n equals 0 to infinity of x to the n. Okay. So if you remember with the geometric series, if x in this case is what we called r before, so we know that this converges to, our formula was a over 1 minus r, where a is the first term and then r is your ratio. So in this case, r is x and a is 1. So this converges to 1 over 1 minus x if the absolute value of x is less than 1. So in other words, x is between negative 1 and 1. Okay. Without, well, we can't have 0 in there. So I guess we'd have to say 1 to 0, union 0 to 1. Wait. Sorry, I'm thinking of the wrong thing. We can't have 0 here because this is a power series. I was thinking about this as being the series and then it being like infinite number of ones, but no, this is the series, right? So you'd have an infinite number of zeros. Anyway, so this is what we got from the geometric series, right? So this will converge to 1 over 1 minus x if x is less than 1. And this is a function, right? So the function 1 over 1 minus x is equal to the series n equals 0 to infinity of x to the n when x is in negative 1 to 1. Okay, so we're taking this rational function and we're representing it as a series of polynomials. Again, very convenient because we know that polynomials are a lot better behaved than the rational function is. So I want to show this graphically. Okay, so I have the graph here. So what I have graphed here is the line or the rational function 1 over 1 minus x, and then this series right here. Obviously, we can't represent an infinite series, but we can represent a finite series. So you can see A tells us how many terms of the series we're going to have. So this is a series with 0 terms. So watch what happens as we slide this slider forward. Okay. As we keep taking steps, it's becoming a better and better approximation of this function. So let me move back here. So it's the purple line is the series. The red line is the original function. Okay. So once we get to like 23, that's pretty much indistinguishable on the keep in mind this is only on the negative 1 to 1 interval, right? That's why it's not moving outside of there. So you know, we can see they become pretty much indistinguishable. So this function is being represented by a series of polynomials. There's a lot of terms in that polynomial, right? It's like x, like at 23, that's like x to the 23rd plus x to the 22nd plus x to the 21st, etc., right? But nevertheless, it's a polynomial. So this is a very powerful idea here, that we can break down all of these functions into polynomials. So once we go to 100, on that -1 to 1 interval, this is pretty much indistinguishable. Okay, so let's look at some variations of this now. So this is just one function. We're going to look at a whole bunch of different functions. Like I said, though, we're going to talk about Taylor series first before we do most of these here. But there's still a lot that we can get just from this one. So some variations we can make on this, for example. Okay, so for example, if we have the function g of x equals 1 over 1 minus x squared, similar function, then using the fact that 1 over 1 minus x is equal to this, if we just do a change of variables here, then we just replace this x with x squared. Okay, and if we simplify that, that's going to be x to the 2n. Okay, so we get a representation of this polynomial now. This rational function now. So we can do this with a lot of different variations of this here. So this is going to converge when x squared is less than 1, which again is going to imply that x is on -1 to 1. Okay, so it's technically a polynomial inequality, so you could solve that and find that out there. Okay. Let's do some more variations here. What if we have the function 1 over 1 plus x cubed? Okay, so now we have a plus in there, and we also have x cubed. Well, we know this is 1 over 1 minus negative x cubed, right? So we kind of get it into that form that we're familiar with. And then we would be able to say that this is equal to n equals 0 to infinity of negative x cubed to the n. So rewriting this a little bit here, we'd have -1 to the n times x to the 3n. So this will converge. This will converge if negative x cubed is less than 1. The absolute value here, we didn't need the absolute value up here because x squared is always positive. But this is also going to imply that x is a -1 to 1. Okay, so no need to do too much there. And now let's look at one more, which is pretty tricky, but we can still get it into this form. So the function here is f of x equals x squared over 4 minus x squared. Okay, so this is pretty different, but we can still kind of see the bones of that form, right? So let's go ahead and see what we can do here. So first of all, the big thing is this needs to be a 1, right? So we're going to need to factor a 4 out of the bottom. So this is going to be 1 minus x squared over 4. Okay. And the top also needs to be 1. So we're going to need to pull that x squared out. So we have 1 over 1 minus x squared over 4. So now that inside part, this part will just kind of bring along with us the x squared over 4. And then this inside part, we know then that is equal to n equals 0 to infinity of x squared over 4 to the n. Okay. And now if you want, you can make this a little simpler. 4 is actually 2 squared. So we can rewrite this. I'm going to bring the x squared over 4 on the outside inside here. And then this is going to be x over 2 to the 2n. Okay. So it looks pretty messy, but I mean, this works, right? We can write it as this. We are just, basically using multiplication and all that. But now determining where this converges might be a little trickier. You might be concerned about this like extra x here, but the series doesn't depend on x at all. So that's ultimately just multiplying it by some number. Okay. So that's not really affecting the convergence of it at all. What's converging is everything that's dependent on this n, because those are the terms that are changing every time. So this is going to converge just like before when x over 2 squared is less than 1. So in other words, x squared over 4 is less than 1. Okay. So we can go ahead and solve that. That's going to give you x squared is less than 4, which will give you that x is less than 2, or x is, x is greater than negative 2 if you take the plus and minus of the square roots. So our interval of convergence here will be from negative 2 to 2, making the radius of convergence 2. Okay, so there's a lot of manipulation we can do. So if there's any way we can get it into this form, ultimately, even if you have extra x's or whatever on the outside, that's fine, because those are essentially just like multiplying it by a constant, right? It's not going to change the convergence. So we can do a lot of different manipulation to get the series into this form, and therefore find a suitable power series to represent these functions.